All right, so in the last video, we got into the topic of logarithms. And what I want to do now is start doing a little bit more with them. The last example was just evaluating logarithms of specific bases with specific arguments and doing a lot of it by hand. But now what I want to do is start looking at some properties of logarithms. I'm not going to prove these here. They're not hard to prove, but that's not the goal here. You would have learned about these logarithm properties back in a college algebra course, and we just want to know how to use them. So these are some of the most important log properties, and what they are used for are expanding or simplifying expressions that involve logs. The first one, if you have a log with any base of an argument that's a product of two things, x, y, but it could also be like 3x or, whatever. There's lots of different variants on this. This is the same thing as log base b of x plus log base b of y. Notice I can take it and split it into two logarithms that are added. So multiplication in your argument turns into a sum of logarithms. Something similar happens with division. If I have log base b of x over y, I get a similar expression, but then now it's a minus. Okay, so this is the result of this. If I'm taking my argument, log base b of x, and I'm raising it to a power of r, you can bring those exponents out to the front of those logarithms so that r can be brought out to the front here. Now it's r times that log, where the argument is just x now. Number 4 is something that we call the change of base formula. If you have a log in a specific base, let's call it c, of x, you can convert this into a problem involving logarithms of any other base that you want using this formula. So this is equal to log base b, where b is any other number, or the same number, it can be the same number, but any number of x over log base b of c. So the base of this logarithm becomes the input or the argument for this denominator's logarithm. The reason this is useful, one of the reasons this is useful is because if you're using a scientific calculator or kind of an older graphing calculator to evaluate the log of something, scientific calculators typically only have two logarithm buttons. They have log, which is base 10, or they have ln, which is base e, the natural logarithm. There typically is no button for a log with a base of 2, or a log with a base of 27, or something like that. So if you have a problem where you have to take a log whose base is something other than 10 or e, how do you do that with a calculator? Well, you use the change of base formula. So you choose a logarithm whose base you can input on a calculator, let that be the b here, and then plug these pieces of information into this formula. That's what that's used for. Okay. All right, so let's do one example where we use some of these properties. I want to expand this logarithm. Right now, I have a single logarithm with a very complicated argument. And what I want to do is expand it out into a sum or difference of several logarithms, but each of which has a simple argument. So let's do this. The first thing I notice is that I have a quotient of two things. And the second of those two logarithm properties said that that's equal to log, in this case it's base 3, log base 3 of 9x squared minus log base 3 of the fourth root of y. I'm actually going to do one additional thing here. That fourth root can be written as y to the 1/4 power. I'm going to use a rational exponent. Okay. What else can I do? Well, looking at this, I have a product of two things here, 9 times x squared. So the first of my logarithm properties says I can write that as log base 3 of 9 plus log base 3 of x squared. Again, minus log base 3 of y to the 1/4 power. Now this has been expanded, but there's a little more that I can do. First of all, this first logarithm has no variables in it, and I can evaluate this one by hand. Think about this for a second. 3 to what power is 9? Well, 3 squared is 9, which means that this logarithm gives us an answer of 2. And then here, I don't know what x is, I don't know what y is, so I can't do the same thing for these two, but each of these has an exponent, which according to that third logarithm property, I can bring it out to the front. So plus 2 log base 3 of x minus 1/4 log base 3 of y. And this is what I would consider to be expanded. Looking at a problem like this, it's natural to ask, why would we bother doing this? Because depending on your perspective, this may look more complicated than this. There's more terms. So how is this better than this? And the answer is something that we'll get to in chapter 2 of our book, called differentiation. We're going to be doing a lot of these things called derivatives in our calculus course. And it turns out that to take the derivative of a function like this requires a lot of work. But taking the derivative of something like this requires significantly less work. And really what it boils down to is how complicated the argument is in this log compared to the argument in each of these logs. So this has a big, big benefit when we're doing derivatives. It's kind of the main reason we want to do that in this class. All right. We talked about graphs for exponential functions. Let's do graphs for logarithms as well. So I didn't superimpose this over the graph of an exponential function, but as we have already seen, in fact, let me go back and do it this way. Exponential functions generally look like this. They're increasing, they're above the x-axis, and they're 1-to-1, so that means that we have that inverse. And we saw that if you want to find the graph of the inverse of a function, you reflect it across the line y equals x. Well, if I took this is y equals 2 to the x, and reflect it across the line y equals x, I get this graph. So now we have something that is to the right of the y-axis, so all of the x values are positive here, but it's a reflection of that exponential function. So it looks like this. One thing worth noticing is that this graph is also increasing. This is the graph of y equals log base 2 of x. So it's the actual inverse of the one we just looked at. It's increasing, but kind of the opposite thing happens as what you saw in the exponential case. Exponential functions with a base that's greater than 1, they will increase at an increasing rate. They're getting steeper and steeper and steeper as you go to the right. Logarithms start out very steep, but as soon as we get above the x-axis, they start getting a less and less dramatic slope. They start to level out more. Now, it never levels out completely, it never becomes horizontal, but it's the rate at which this thing is increasing gets really, really small very quickly. Based on this graph, we see a couple of things that are worth mentioning. The domain of this graph, remember the thing that all the values you're allowed to plug in are only the positive real numbers, so 0 to infinity, that's the interval we would write. The range of this function is all real numbers. This goes down forever this way, and even though this grows very slowly, it does hit all of the positive real numbers. I think I was off screen a little bit there. So this grows kind of towards infinity, which will make more sense of that later on in the course. This is not a surprise because remember, basically what inverses do is they take your original function f of x and they swap the inputs and outputs. So the domain and the range swap places. The domain of an exponential function is this, and the range is this, but now those have swapped roles. Okay? As we did with exponential functions, it's worth looking at a logarithm that has a base that's less than 1. It has to be a positive number still, but the base is less than 1. And we would like to see how that affects the graph. So let's do that here. Sorry, I got a lot of papers here. This is what the graph of y equals log with a base of 1/2 of x looks like. And as we saw with the exponential function, we no longer have an increasing function in this case, we have a decreasing one. So it starts off very steep, but decreases this direction, okay? So to generalize, if you're looking at the graph of y equals log base b of x, you're gonna have an increasing function if that base is greater than 1, and a decreasing function if that base is between 0 and 1, similar to what we saw with exponentials, okay? And then finally, a way of writing that inverse relationship between the two things, exponentials and logarithms, is this. This is something that's important for solving equations, which we're about to do. If you take log base b of b to the x Or if you take b to the power of log base b of x, in each case, the exponential and the logarithm cancel each other out and just leave you with that x. That's what this is saying, and that's what inverse functions are supposed to do. All right, coming to the end here. So we want to do a couple of examples where we have to use logarithms to solve a problem. So the first thing I want to do is solve this equation right here. E to the x times e to the x minus 4 equals 12. So the way I'm going to approach this, I'm going to start by distributing that e to the x in. E to the x times e to the x would be e to the 2x. I'm using an exponent property here. And hopefully you know that exponent property. I can add those exponents. Minus 4 e to the x equals 12. The next thing I want to do is get a 0 on this side. If I subtract 12 from both sides, I get e to the 2x minus 4 e to the x minus 12 equals 0. Now, from here, if you remember solving these types of equations in your college algebra or your pre-calculus class that you took, this should feel kind of familiar, but if it doesn't, this is something I call a quadratic in disguise. So you remember in the previous video, we talked about how sometimes it's helpful to make a variable substitution. If I were to set y equal to e to the x, and then make some substitutions in this expression, I can turn it into a quadratic equation, which we have lots of techniques for solving. Notice the e to the 2x here is the same thing as e to the x squared. And that's important because if y is equal to e to the x, I can change this thing into a y so that my first term here becomes y squared minus 4. Remember, e to the x is y, so I'm going to call it 4y minus 12 equals 0. This quadratic is factorable. It turns into y minus 6 times y plus 2. That's equal to 0. Okay. This tells me that either y is equal to 6 or y is equal to negative 2. That's how we would solve this. You set each of these equal to 0 and solve them, I would get this. But remember, it's not y that we're trying to solve for, it's x. So now I take this thing that I defined over here and substitute the e to the x back in for those y's. E to the x is equal to 6 or e to the x is equal to negative 2. All right. Now this looks like I have two possible solutions, but one of them doesn't give me anything. This one right here, e to the x equals negative 2. If you remember, we said that exponential functions cannot give you negative numbers. There is no value of x that would ever make this true. No real value anyways. So this gives me nothing useful. I only need this one. How do you solve this? Well, you take a natural logarithm. Remember, if I take the natural log of both sides, natural log of e to the x, they cancel each other and just leave me with x. If I take the natural log of this side, I get x equals the natural log of 6. And here we talk about kind of an important convention. Generally speaking, when we take the natural log, or really any log of a number that's not easily evaluated, if it's something that would give us like a really nasty decimal, we tend to just leave it in that form. So I leave that natural log, that ln, written that way. I'm not necessarily going to go plug it into a calculator to get a decimal. Now, there are some cases where you do want to do that, particularly, problems like these continuously compounded interest problems. We're about to do one of those where the number that you're getting represents some number of years or a dollar amount. Basically, application problems are where you want to plug that into a calculator. But if it's just solving an equation or something like that, it's preferable to leave it in that form. So that's what I'm going to do here. That's our solution. All right, last problem. Compound interest problem. It's got an A and a B to it. So let's start with A. We're going to make a one-time investment of $1,000. So that's P equals 1,000 in an account that earns 6.8 interest annually. So that's my rate. R is equal to 0.068. And it says, how many years will it take for your investment to double if interest is compounded monthly for part A and continuously for part B. So for part A, monthly means that we're compounding our interest 12 times per year because there's 12 months in a year. That's what n is equal to. I don't know the number of years that I'm plugging in. I don't know t, because that's the thing I'm trying to find. I do know, however, what my account balance should be for the number t that I'm looking for. It's whatever I get from doubling my investment. Well, if I double 1,000, I get 2,000. So I get A is equal to 2,000. Now I can plug things into my compound interest formula. So 2,000 is equal to my principal, 1,000, times 1 plus r over n, so 0.068 over n, which is 12. And then I'm going to raise that to the power of n, again 12, times t. And we don't know t, so we just call it t. If you notice, what I have here is an equation where there's only one unknown in that equation, t. I can solve this for t, but solving this for t is going to require at some point a logarithm. So here's where we're going to kind of work through those steps. I'm going to start by dividing both sides by 1,000, so I get 2 equals 1 plus 0.068 over 12. Now I'm actually not going to plug this into a calculator yet. I'm going to keep writing this expression over and over again because I want to save all of the calculator work for the very end. And the reason we do that is because it avoids something called compounding rounding error. Basically what that means is if I plug a number into a calculator, there's a chance that I get some big long decimal that I have to round. So that right away means that if I'm rounding that decimal, I have a number that's not exactly equal to the correct answer I'm looking for. If I use that number in more calculations in later steps, then I'm using an incorrect approximation. And every time I use that, there's a chance that the error in that approximation gets bigger and bigger. We can mostly avoid making that really bad if we wait until the very end to plug things into a calculator. So here's where we're at. 12t there. Okay, how do I solve for t? Well, I need a logarithm because logarithms are how we solve for unknowns in exponents. Now, the straightforward thing would be to use a logarithm with a base of whatever this is, because then it would cancel this out. But the problem is, I can already see that this number in here is not equal to 10, and it's not equal to e. So when I get to the step of having to take a logarithm, I don't have a button on my calculator for that. I do have a button on my calculator for the natural log, though. So what I'm going to do is take a natural log of both sides. Natural log of 2 is equal to the natural log of 1 plus 0.068 over 12 to the 12t. Now, even though that natural log doesn't just cancel the base out, it does allow me to use that property of logarithms where you can take the exponent out to the front here. This is equal to 12t times the natural log of 1 plus 0.068 over 12. Sorry, it's kind of sloppy right there. I started writing a parenthesis when I meant to write an L. Okay, that's not a plus, that's a t. Okay, so to solve for t, I just need to divide by 12 and this natural logarithm. So what that gives me is t equals, we had a natural log of 2 on this side, over 12 times the natural log of 1 plus 0.068 over 12. Now it's a little bit tedious to have to keep rewriting this expression over and over again, but this is where I actually want to plug things into a calculator. I don't really want to leave t in this form because I can't look at that and think, oh, that's about 12 years or 5 years. Yeah, I can't see what that's approximately equal to. So as an application problem, we do want a decimal from this. This would go into a calculator, plug it in exactly as you see it. This comes out to approximately 10.22. And this is years. Okay. So that's good. We have an answer for that one. Let's look at part B. Same information, the only difference is that we're compounding interest continuously. That's where I use that PE to the RT formula. So I have the same principal, the same rate. we're still looking for t. So I'm not going to rewrite this information. It's the same. We're also looking to double our investment, so A is still equal to 2,000. So 2,000, our account balance is equal to P, 1,000, E to the RT. That's 0.068 T. Okay. Same first step, divide by 1,000. That would give me 2 over here, E to the 0.068 T over here. Now, to solve for this, I would do the same step that I did in the previous problem. I'm going to take a natural log of both sides. Only this time, I actually have the ideal base on this exponential to be using a natural log, because the natural log has a base of e, which means these things actually do cancel each other out. I get 0.068 t. So divide both sides by 0.068. I get the natural log t equals the natural log of 2 over 0.068. And again, a little less to punch into your calculator, but that's what you're going to do next. You're going to plug that into a calculator. And I get t is approximately 10.19 years. Okay. It's worth comparing these two answers to kind of see how continuously compounded interest compares to other compounding rates. So as you can see, continuously compounded interest is better than monthly interest because we double our money in less time, 10.19 compared to 10.22, but very, very little difference between those at the same time. And really that goes back to that table that we saw when we came up with E in the first place. So I'm going to return to that table for a second if I can find that page. It should be over here. Here it is. Here's where we came up with E, right? We plugged different values of n into this expression. Well, when n was equal to 12, remember that's like monthly compounded interest, we got 2.613035. When I plugged in something really big, or if we just go straight to where E was equal to 2.7182, blah, 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 blah. These two numbers are pretty close. So the benefit of continuously compounded interest, where we use an E instead of a 12 for n, is better, but marginally so. Okay, so that's kind of a good comparison between those two things. This is going to wrap up our review on exponential and logarithms. Exponentials and logarithms. Starting next week, we'll be doing some actual calculus with the topic of limits.